So here we're going to take a brief look at the acetoacetic ester synthesis. This, very much like the malonic ester synthesis, is a useful reaction, but it's a very, very special case reaction. And in general, the entire purpose of this reaction is to make substituted acetones. Acetone doesn't end up working so great for alpha substitution. It typically will want to perform an aldol condensation in a lot of situations, and so we use this reaction instead. What happens here is we start with this dicarbonyl. First step, we treat with base, followed by our electrophile. And then in the second step, base, and then acid with heat. And what we get as a result this is why we call it an acetone derivative, because this piece of the molecule, which is basically a substituted acetone. And then our electrophile here will be bonded at the alpha carbon. So clearly a lot going on here, including probably the question of where did our other carbonyl group go? So a lot of steps that you've likely seen before, and then one very, very unusual step. And it's that unusual step that gets rid of the ester group. But the first part of this mechanism is just an alpha substitution. So we add in a base. In this case, we're using sodium methoxide. And we use that base to match what's on our ester that's already there. If we don't use that, then it can react there as well, and that could have an effect on the reaction. But in this first step, again, all we're doing is making an enolate. It's a relatively easy enolate to form. Because that alpha carbon is actually alpha to two carbonyls, and so really easy to remove. We can then add in an electrophile. We'll use methyl iodide here, just so our drawing doesn't get too cluttered. And we get substitution. This is just an alkylation reaction. An SN2 attacking the methyl iodide, kicking out the iodine. And we've done our first part of this reaction, which is that we've successfully alkylated the alpha carbon of this compound. All right, so what happens next? Well, the next piece, we add sodium hydroxide, and that's going to be a section that you're also familiar with the mechanism, hopefully. Because what happens if we add sodium hydroxide to an ester? Hopefully, you've said that we get a hydrolysis to take place. Hydroxide attacks the carbonyl, electrons up onto oxygen, then the electrons on oxygen reform the carbonyl, kick out the leaving group, and we've made our carboxylic acid. Now recall that at this point, we've still got base present, and so it's going to deprotonate the carboxylic acid until we quench with acid. But now that we have quenched with acid, we're ready for the final step, which is going to get rid of that second carbonyl. So notice, while this mechanism is a lot of steps, and we've actually still got a few more steps here, so far it's just been a combination of two reactions, which you're likely already familiar with. We started with an alkylation on the alpha carbon, and our second step was hydrolysis of the ester. So how do we finally get rid of that carbonyl? So this is going to be the same structure that I had on the previous page, just rotated around the one carbon-carbon bond to make this easier to see. But if we heat this, we have that six-membered ring that you can see. The carbonyl grabs that proton, the OH electrons add in, form a double bond, and we break that carbon-carbon bond. And what happens to the other carbonyl? Well, it just got released as carbon dioxide. So we're almost done. One final step. What's that final step? Well, we now have an enol. And enols, in most cases, if they're exposed to acid or base, and this last step happens with sulfuric acid, are found to be much more stable as their carbonyl. So oxygen reforms the carbonyl. These electrons pick up a proton. And finally, loss of a proton yields our carbonyl. And as you can see, what we've revealed is basically acetone that we've added some sort of alkyl group to it. So again, this reaction is useful in very, very specific situations. We can vary the R group here. It doesn't have to be methyl, so it doesn't have to be exactly acetone. And then we can use any electrophile that's good in an alkylation or an SN2 reaction. But it's a good way to make substituted acetone derivatives. Definitely one of your longer mechanisms that you'll learn in this course. But fortunately, the only step that's really new is this, sort of rearrangement type step. Otherwise, the other three parts to this reaction, alpha substitution, ester hydrolysis, and then at the end, enol conversion into the carbonyl.